Welcome to the Shikasa Boo Motor channel. This channel provides easy-to-understand explanations of car mechanisms. The Toyota RAV4 Hybrid and the Honda CR-V Hybrid compete head-to-head. Let's take a look at the specs of these two vehicles. Their dimensions are almost identical. Both are powered by inline-4 gasoline engines, with 2.5 liters of displacement in the RAV4 and 2.0 liters in the CR-V. While the Toyota RAV4 has higher engine output, the Honda CR-V has the advantage in traction motor output, especially maximum torque, where the difference is overwhelming. However, the Toyota RAV4 has two traction motors. When it comes to fuel economy, the RAV4 has the advantage, but the CR-V is often regarded as having better acceleration feel. These differences stem from the distinct hybrid and AWD architectures utilized by the RAV4 and the CR-V. In this video, we'll explore the hybrid systems and their operation, the differences in AWD systems, and the advantages and disadvantages of both vehicles. The CR-V employs a two-stage series parallel hybrid system. Honda brands this system as two-motor hybrid or EHEV, depending on the market. This system consists of an engine, a generator, a lock-up high clutch, a traction motor, a lock-up low clutch, and a differential. Except under certain driving conditions, this system operates as a series hybrid. The engine is used solely to power the generator and is not involved in propelling the vehicle. The traction motor propels the vehicle, using electricity supplied by the hybrid battery or the generator. Electric motors used in hybrid vehicles and battery EVs become less efficient at higher rotational speeds. For this reason, the system transitions to engine mode during steady cruising at highway speeds. The CR-V features a two-stage engine mode, and during highway cruising, the lock-up high clutch engages. Engine output is transmitted to the differential via the clutch, allowing the vehicle to cruise within the engine's high efficiency range to improve fuel economy. In this mode, the reduction ratio is 0.707, which is comparable to the top gear of a conventional transmission. The lock-up low clutch engages at low to medium speeds to enhance towing capability. The reduction ratio is 1.409, which is comparable to third to fifth gear in a conventional transmission. In markets where towing capability is not required, Honda explains that the low clutch is utilized for gentle urban acceleration and hill climbing. However, in practice, the clutch may not be strictly necessary for these purposes. The RAV4 employs a power split hybrid system. Toyota brands this system as Hybrid Synergy Drive or THS2, depending on the market. This system consists of an engine, a planetary gear power split device, MG1, which mainly functions as a generator and starter motor, MG2, which primarily propels the vehicle, and a differential. MG stands for motor generator. Now, let's take a closer look at the relationship between the engine, the two motor generators, and the planetary gear set. The engine is connected to the planetary carrier, while MG1 is connected to the sun gear. MG2 is connected to the gear teeth on the outer circumference of the ring gear via an intermediate gear. The system operates in EV mode from launch to low-speed driving. The engine remains off, and MG2 propels the vehicle using power from the hybrid battery. When the vehicle speed exceeds a certain threshold, MG1 acts as a starter motor to start the engine. When the engine starts, the system transitions to engine mode. In this mode, the planetary gear set of the power split device operates as a CVT, continuously variable transmission. The system varies vehicle speed by controlling the sun gear speed while maintaining a constant engine speed. If the generating power of MG1 is increased and the rotational resistance becomes larger, the sun gear rotates more slowly and the ring gear rotates faster. This is the high gear condition. When the generating power of MG1 is reduced, the rotational resistance decreases. This allows the sun gear to speed up while the ring gear rotates more slowly. This is the low gear condition. During highway driving, electrical power is supplied to MG1 to drive the sun gear in reverse, causing the ring gear to rotate at an even higher speed. This is the top gear condition. At this time, MG1's torque is added to the engine torque to drive the ring gear. Simultaneously, this additional torque is transferred to MG2 for electricity generation. This generated power is then fed back to drive MG1. Of course, some losses occur in the process, but circulating energy in this way allows the system to change the gear ratio efficiently. Because this control is performed continuously and seamlessly, the engine can maintain its most efficient speed range, delivering superior fuel economy. During acceleration, MG2 assists the engine as needed. Let's briefly summarize the power flow of the two hybrid systems. Except in certain driving conditions, such as high-speed cruising, the CR-V is propelled by the electric motor. This means that the driving performance is determined by the output of the electric motor. Except during low-speed driving, the RAV4 is propelled by the combined power of the engine and the electric motor. Now, back to the specifications table. The CR-V's engine produces only about 80% of the power and torque compared with the RAV4. Since the engine's primary role is to power the generator rather than propel the vehicle directly, Honda determined that this output was sufficient. On the other hand, the CR-V's traction motor is much more powerful, as it is solely responsible for propelling the vehicle. However, the RAV4 also features a motor on the rear axle. Just how much power the rear motor actually delivers during everyday acceleration is something only Toyota's engineers truly know. The CR-V features a mechanical AWD system with a propeller shaft. The output from the engine and the traction motor is distributed by the transfer unit to the front differential and to the rear differential via a propeller shaft. An electronically controlled hydraulic clutch type AWD coupling is installed at the front of the rear differential. Under normal driving conditions, the AWD coupling disconnects the rear differential from the powertrain, and the system operates as FWD. When necessary, the system variably controls the clutch engagement force of the AWD coupling to distribute drive torque to the rear wheels. The drive torque is distributed between the front and rear wheels, from 100 to 0 to 50 to 50. The RAV4 features an electric AWD that uses a dedicated rear drive motor. When necessary, the system supplies power to the rear motor and distributes drive torque to the rear wheels. The drive torque can be distributed from 100 to 0 to 20 to 80. The RAV4 delivers superior fuel efficiency compared to the CR-V. Let's explore the reasons behind this. Toyota claims the A25A FXS engine in the RAV4 has a maximum thermal efficiency of 41%. Although the engine does not achieve 41% under all operating conditions, we will simplify the discussion here and assume a thermal efficiency of 41%. When the RAV4 is cruising at a constant speed on a suburban road, the engine propels the vehicle. If we ignore gear losses, 41% of the energy in the gasoline is used to propel the vehicle. What about the CR-V? Honda also claims that the LFC2 engine used in the CR-V has a maximum thermal efficiency of 41%. This engine operates at 41% thermal efficiency and drives a generator to produce AC power. We will assume the generator efficiency is 95%. This AC electricity is converted into DC by the inverter. We will assume the inverter efficiency is 97%. To drive the traction motor, this DC electricity is converted back to AC by the inverter, with an efficiency of 97%. The traction motor is driven by this AC electricity. Its efficiency is 95%. As a result, the calculation becomes 41% times 95%, times 97%, times 97%, times 95%, meaning that only about 35% of the energy in the gasoline reaches the wheels. Why does the system need to convert AC to DC and then back to AC again? This isn't strictly accurate, but roughly speaking, the traction motor speed is controlled by the frequency of the AC applied to it. At lower frequencies, the motor rotates more slowly, while at higher frequencies, it rotates faster. In this system, the AC produced at a frequency determined by the generator speed is first converted to DC, and then converted back to AC at a frequency suitable for the traction motor speed. In addition, the CRV system requires a hydraulic pump to actuate the lockup clutches. Although it varies by vehicle and driving conditions, the loss from an automatic transmission oil pump is roughly comparable to that of an air conditioning compressor. The RAV4 system also has an oil pump, but its purpose is to lubricate and cool the motor and gears, so it does not need to generate high hydraulic pressure. We all know from experience how much fuel economy changes, depending on whether the air conditioner is on or off. From a fuel economy standpoint, the CRV series parallel hybrid system fundamentally cannot compete with the RAV4's power split hybrid system. There's more. When driving in FWD mode, the CRV still has to rotate a heavy propeller shaft that does no useful work. This also leads to substantial energy waste. Some vehicles, such as the Ford Escape and previous generation RAV4, feature a mechanism that disconnects the propeller shaft from the powertrain to avoid this loss. But the CRV does not. As a result, the CRV's fuel economy is about 10% worse than the RAV4's in the EPA rating, and about 20% worse in the WLTC. The CVT in the RAV4's hybrid system, although completely different in structure, is functionally similar to a conventional belt-driven CVT. The accelerator pedal is pressed. The transmission increases the gear reduction ratio. The engine speed rises. And then the vehicle speed increases while the engine speed remains constant. This is the infamous rubber band effect that many drivers dislike. In the RAV4, MG2 powers the vehicle from launch through low speeds and assists the engine in engine drive mode. As a result, the rubber band effect is significantly improved compared to typical belt-driven CVTs. Most drivers will have no complaints, but a rubber band is still a rubber band. On the other hand, the CRV is driven by the traction motor for most of its driving. This graph shows the torque characteristics of typical electric motors. Electric motors produce their maximum torque from 0 RPM through the low to mid-speed range. In the CRV, the moment you step on the accelerator, 335 Newton-meters, which is 247 pound-feet of torque, pushes you back into your seat. This is comparable to the maximum torque of a typical 3.0-liter naturally aspirated 6-cylinder gasoline engine. There is no rubber band between the accelerator and the drive wheels. Let's take a closer look at how these two AWD systems work. As previously discussed, the RAV4 features an electric AWD system, while the CRV employs a mechanical one. The CRV distributes torque via the AWD coupling, resulting in a 100-to-0 split when the coupling is free, and a 50-to-50 split when it is locked. The coupling is an electronically controlled hydraulic multiplate clutch, based on various signals from wheel speed sensors, the steering angle sensor, and others. The ECU calculates the optimal torque in real time, adjusting the clutch for variable distribution. In the RAV4, The dedicated rear motor operates independently of the engine and MG2, enabling a front-to-rear torque distribution ranging from 100 to 0 to 20 to 80. The ability to bias torque toward the rear wheels is one of the RAV4's strengths. The CR-V's traction motor produces a maximum torque of 335 Nm or 247 pound-feet, allowing up to 168 Nm or 124 pound-feet of torque to be applied to the rear wheels. Since the RAV4's rear motor produces a maximum torque of 121 Nm or 89 pound-feet, the CR-V has the advantage in this regard. Modern AWD systems operate as integrated systems that include not only the powertrain layout but also electronic brake control. Therefore, their real-world performance cannot be judged by specifications alone. To see these systems in action, try searching for comparison videos of the two vehicles on YouTube. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.